Welcome AP Chem students. In this next video we're going to be looking at comparing pHs of different mixtures, and so we're going to do one set of questions where we're looking for the mixture with the highest pH and then one for the mixture with the lowest pH. First we're doing the highest pH, so when you see that you need to remember we're looking for the one that is most basic. Okay. Alright, so in the first one we're comparing sodium acetate and copper 2 nitrate. So sodium acetate, NaCH3COO, copper 2 nitrate, CuNO32. Alright, so we need to evaluate what's in our two different mixtures. In sodium acetate we've got sodium, which is a spectator. We know it's a spectator because it is the conjugate acid of a strong base, and conjugate acids of strong bases are extremely weak to the point that they are simply spectators. We also have another spectator in the copper 2 nitrate solution. The nitrate is also a spectator. And again, we know it's a spectator because it is the conjugate base of a strong acid, meaning that it is extremely weak. So now, what we really need to be comparing in the two different solutions is the acetate versus the copper 2 ion. So acetate is a stronger conjugate base because it came from a weak acid, acetic acid. So it means that it is going to take some hydrogens from water and it's going to generate some hydroxide ions. On this side, we've got the copper 2 ion. This, since it's a smaller ion, if you look at its position on the periodic table, also that it's got a +2 charge, we consider this an acidifying cation, meaning that it is actually going to attract some hydroxides towards itself from water, meaning that it will generate some hydrogen ions. So, in this case, the most basic one is going to be our sodium acetate solution. Alright, let's move to our next example. We've got 2 molar potassium carbonate and 2 molar lithium iodide. So potassium carbonate is K2CO3, lithium iodide is LiI. And looking again, let's figure out spectators. Why is potassium a spectator? Because it would be the weak conjugate acid of a very strong base, potassium hydroxide. And then over here, iodide is also a spectator because it would be the conjugate base of a strong acid, hydroiodic, so it is so weak it's a spectator. Alright, we also have another spectator here. The lithium is also a spectator. And the reason why it is also a spectator is because it would be the weak conjugate acid of a strong base, lithium hydroxide. So, as far as this one goes, we're going to consider this one probably to be pretty neutral. But over here with the carbonate, we know that that one is a stronger conjugate base, meaning that it's going to snap up some hydrogens from water, and it is going to generate some hydroxide ions. So therefore, this one is going to be the most basic, so it's going to have the higher pH. Alright, next we're going to look at 2 molar ammonium fluoride versus 2 molar sodium fluoride. So NH4F versus NaF. Alright, let's identify some spectators. In NH4F, neither of those would be considered a spectator because NH4 is the conjugate acid of a weak base, so this is a stronger conjugate acid. And then fluoride ion would be a stronger conjugate base because it would have come from hydrofluoric acid, which is a weak acid. Now over here with the sodium fluoride, we've got just let me change colors of that. Sodium is our spectator because it would be the weak conjugate acid from a strong base, NaOH. And then fluoride, just like over here, is one of our stronger conjugate bases. So, in this case, since sodium's not doing anything, fluoride's a stronger conjugate base, which means it's going to snap up some hydrogens from the water that it's in. So this one is actually going to generate some hydroxide ions. Over here with the ammonium fluoride, alright, the ammonium is going to generate some hydrogen ions because it's a stronger conjugate acid, which means it'll get rid of some of its hydrogen. Stronger conjugate base over here is going to generate some hydroxide, and really what happens is that the hydrogen, the extra hydrogen from this, is snapped up by the fluoride, so really it ends up being neutral. So our larger pH is going to be our sodium fluoride. It'll be more basic. Moving on to our next example, calcium oxide in water or sodium chloride in water. So calcium oxide in water is one of those things you should recognize. Whenever you put a metal oxide in water, it's going to give you a metal hydroxide. And then sodium chloride in water is just going to give you sodium ions and chloride ions. Well, remember that sodium is a spectator ion. We talked about that a moment ago. Chloride is also basically a spectator because it is the very weak conjugate base of the strong acid hydrochloric acid. So we would expect sodium chloride in water to be neutral. However, over here, since we're going to have calcium hydroxide in solution, we have the generation of hydroxide ions in solution because calcium hydroxide is one of our strong bases. So our calcium oxide in water is going to have the larger pH or be more basic. Alright, and our last one, picking out the most basic one, we've got SiO2 in water. Or we've got copper 2 nitrate dissolved in water. Now, why didn't I write the SiO2 as aqueous? We should remember that silicon dioxide, better known as quartz, better known as sand, or as glass, is a covalent network solid, meaning that it doesn't dissolve in water and it has an extremely high boiling and melting point. So, since the SiO2 does not actually dissolve in the water, this is going to be a neutral solution. Now, over here with the copper 2 nitrate, we actually looked at this a little bit earlier. The nitrate is basically a spectator ion because it is the very weak conjugate base from the strong acid nitric acid. But our copper 2 is an acidifying cation because it is a smaller cation with a larger charge, which means that it's going to take some of the hydroxide out of water and it's going to generate some hydrogen ions. So, therefore, this one's actually going to be more acidic. It's going to have a lower pH. So, neutral in this case would have the higher pH. Alright, now we're going to switch gears and we're going to look at which one has the lowest pH, and so we're looking for most acidic. Alright, so in our first one, we are comparing magnesium sulfate and lithium carbonate. Now, spectator ions, we've got some lithium. Let's make that red. Alright. Lithium's not going to do anything because we can think of it as being the very weak conjugate acid from a strong base, lithium hydroxide. So keep in mind all of those group 1 metal ions and then calcium, strontium, and barium from group 2 are always going to be acting as spectator ions because they are the conjugate acids of what would be a strong base. All right, and then over here, sulfate is going to be another spectator, very, very weak. And so now we have to look at what's going to be going on from the other side. So magnesium is considered an acidifying cation because it is a smaller ion with a larger charge. So that means it's going to generate hydrogen ions. Over to our other solution, we've got carbonate, which is a stronger conjugate base because we can think of it as being the conjugate of carbonic acid. So some of it is going to snap up some hydrogen ions, and that is going to cause it to generate some hydroxide ions. So this time we are looking for most acidic, so the thing that's going to generate extra hydrogen ions is going to have the lower pH for being more acidic. Alright, next we are looking at ammonium chloride and sodium chloride. Now you may remember that we established earlier that both of those are basically going to be spectator ions because it's a weak conjugate acid, weak conjugate base, and so this is going to be neutral. Now on the other side, we've got chloride, which again is a spectator, but then we've got ammonium, which is a stronger conjugate base because we can think of it as not conjugate base, but conjugate acid, rather, because we can think of it as being the protonated form of ammonia. So that means that this is going to be able to generate some hydrogen ions in solution, so that's going to make it more acidic. Alright, for our next one, again with the sodium chloride, and this one's sodium fluoride. So again, spectators with a neutral solution. And then we got sodium as a spectator again. But fluorine is a stronger conjugate base because we can think of it as being the conjugate base of a weak acid, hydrofluoric acid. So it is going to take some hydrogens from water, which causes it to generate hydroxide ions. So in this case, since that is going to have a higher pH, we're looking for the one with the lower pH, the neutral will have the lower pH in that case. Right, next we are looking at magnesium nitrate and potassium chloride. Now, potassium chloride, we've got two spectators because potassium can be thought of as the very weak conjugate acid of potassium hydroxide. Chloride is the very weak conjugate base of a strong acid, hydrochloric acid. So that solution is going to be neutral. Now over here with the magnesium nitrate, we've got the nitrate spectator because conjugate bases of strong acids are very, very weak, and nitric acid is a strong acid. And then magnesium, we said this earlier, it's a small ion with a larger charge, so this is an acidifying cation, meaning that it is going to get some of the hydroxide from water and generate hydrogen ions. So that means that one is going to be the more acidic of the two. Almost finished here. Alright, nickel 2 nitrate, so NiNO3 in parentheses 2, or calcium nitrate. Similar formulas. Alright, we both got nitrate going on. We talked just a moment ago about how they are basically going to be a spectator ion in solution. All right, nickel. Nickel is an acidifying cation because if you look at its position on the periodic table, it is one of the smaller ions. Also, it's got a larger charge, it's a +2, so that means it's going to take some hydroxide from water and generate some hydrogen ions. Over here, calcium is actually going to be another spectator because we can think of it as being the very weak conjugate acid of calcium hydroxide, which is one of our strong bases. So this solution should be about neutral. And so therefore, the nickel 2 nitrate solution is going to be the more acidic of the two. All right. Last one, carbon dioxide and water, or oxygen gas and water. Okay, so when carbon dioxide and water come together, you get carbonic acid. But oxygen and water, it just gives you some aqueous oxygen gas. Actually, I should have said gas there. Sorry about that, I hit the wrong button. That should have been AQ, as I was saying. So for this, the presence of oxygen and water does nothing to it. So it's still going to be neutral. However, putting some of this into water means that since this is a weak acid, there's still going to be some of it that will generate some hydrogen ions as it dissociates. So that one is going to be the more acidic of the two or have the lower pH. So thank you for watching and good luck.